All right, thank you for the introduction and hello all. Good evening to everyone. I'm Arun Bagavathi. Since you all know a little bit about me, I thought I could use some information from you all. So I have a small poll set up. It's just a simple question, totally anonymous. I just want to know, what's your background are, and so that will help me to choose my words carefully. Hope that is okay. So I'm opening up the poll now. If you can participate in the poll, it will be super helpful for me. Yeah, there we go. People are participating. Yeah, this is useful. A lot of folks from deep learning, machine learning, AI background. So yeah, that is informative. So I will keep the poll open. So just in case if anybody else wants to participate. So let's start my talk, and the agenda for today are the following. First, I will talk a little bit about HPCs, supercomputers, what's the purpose of them, what are them basically, and a little bit about big data, the current state of big data, and what are all the emerging paradigms of computing, emerging in the sense, what are all already existing and how they are being used in our day-to-day lives. And then we will go a little bit into artificial intelligence, what we are doing at OSU with artificial intelligence, and combine it with real-world applications. And then the future. I have a star over there. I will let you know what that star in the upcoming slides. But that's the total plan for this session. I will. I would like to start the talk with some quotes from top tech experts around the world, from Google and Facebook. Pretty much all experts and all researchers can agree to this. We need more computing power. When if you look at where we started, where when the computer was built, and where we are now, it's a tremendous improvement over years, and people have worked hard to make systems efficient, make computing efficient, make them more portable, scalable, and reliable. So computing is very necessary in our day-to-day lives, and also in emerging fields like natural language processing, computer vision, and AI. So being said that, there is a popular hypothesis called the Moore's law. Moore's law was true for some time. Moore's law basically says, the number of transistors in the computer chips. So our computers, our processors basically are made of computer microchips, and those microchips in turn hold transistors. So those transistors approximately doubles every couple of years, and that leads to exponential growth in computations, and developing algorithms, and creating more efficient systems. It's been true. So if we look at where we started, before the original times of computers, we started with 90 nm processors, 90 nanometer, right? And if you look at the chip sizes, you can see where we are now. Right now, I think we are at 3 nanometer processors, so which is a huge improvement in less than a century. Right. So the field is so fast. People are investing a lot in developing these microchips and transistors, and making them very small, but adding more power to that. So let's look at a processor which you all can relate. For example, the Mac machines. Right. So the Mac processors, Apple processors, by the time when they started by 2010 or 2012, the number of transistors were around 1 billion. Right, so 1 billion equals to I think 100 crores, and you can see how much we have improved over time. And right now we have I think M3 Max and M3 Ultra. M3 Max has 92 billion transistors, and M3 Ultra, I think it has around 160 billion transistors. Right. The research is not going to stop over there. It's still going to improve. I think there is still hope to develop these processors for the next decade or two. So it's still good, but the only thing is we don't know if Moore's law is true anymore, right? So we are developing these transistors and processors very rapidly, and it's very difficult for Moore's law to keep up the pace of our developments. So there is a debate going on that Moore's law is already over, and people are starting to think about what's going to be the case, post Moore's law. Moore's law is very important. Why? Because it kind of tells us where our computational power will be in the future if the hypothesis is true, right? So if that hypothesis is false, then what's the alternative? We cannot fit our computing power in our hardware. So what are we going to do? Our usage of internet is increasing, our IoT devices are increasing, our population is increasing. So how are we going to keep up with the speed of all these users, right? So we need definitely alternatives, and that's where the ideas like quantum computing and other types of computings chime in, right? So I just want to give highlights on two high performance computers and supercomputers. One is I took this example from my university's high performance computing. I don't know about Indian universities. I'm not that aware of, so I just went with OSU's high performance computing. So you can see, what this high performance computer is. High performance computer is nothing but multiple clusters put together. So each cluster may have their own configuration. For example, one cluster would have more GPU power. Another cluster would have more CPU power. Another third cluster may have systems developed for distributed computing like Hadoop, Apache Spark, and so on. And you can think of many possibilities. So if you take OSU Speed, for example, they have around 4 clusters. One cluster just for just regular computing purposes. The second cluster for high performance computing, and the third cluster for even more larger memory. And there are other clusters as well. So together you can see how many processors and how much memory in total they have in addition to the massive storage present with them. Now, if we want to compare this HPC, HPCs people develop to provide reliable infrastructure for an organization like university or tech companies. Right now, you take this. This is considered as a small scale HPC. Now, if you want to compare this with the super fast supercomputer, this is the world's fastest supercomputer, as far as I know. It's been available from December 24, but not for the public. Only for U.S. nuclear weapon research. Right now, you look at the configuration or specs of this supercomputer. Right, so they have around 11 million CPU plus GPU cores and 11,000 nodes, like 4 compute engines in each node. Right, so this is massive, and they are not going to use this for any standard research. This is more dedicated towards U.S. nuclear weapon research and running simulations on nuclear weapons. This makes sense, right? So the country cannot simply go out and test a random nuclear weapon, compromising safety and compromising, people's health, right? So it is necessary to develop supercomputers like these to run simulations. So this tells us how the supercomputers are important for every aspect of our large scale computations. Right. By the way, you can stop me anytime if you have any doubts or questions. My slides are just overview on the advanced computings. So if you have any basic questions, please feel free to stop me anytime and ask questions or post your questions on the chat. So now talked about HPCs and supercomputer. There is a small difference between HPCs and supercomputer, right? Sometimes people use them interchangeably, but according to me, they have smaller differences. One is supercomputers are dedicated for uh, for for one purpose, right? So they are dedicated for or certain applications. Like for example, in this case, the El Capitan is dedicated towards U.S. nuclear weapons research. Right? But if you check the high performance computing can have multiple clusters. So multiple groups can actually access the HPCs and make use of the resources they offer. All right. So HPCs in turn could have supercomputers as one of their clusters. So that supercomputer could be used for some dedicated purposes. So that's the basic difference between HPCs and supercomputer, according to me. That could be other pointers as well, but this is the main difference that I could think of. Now, why should we have our HPCs and supercomputers? The main reason is the term called big data with capital B, right? So we invented this term, big data, I think 15, 20 years back. I think so. Hope I'm not wrong. What is big data? Big data is data that is so big. That's the basic definition I usually get from my students. But yeah, we will look at some technical definition in the next slide. Being uh, being people that that heard of this term for quite some time, I just want to run a quick icebreaker and see what you think the amount of usage in internet that we have. So I'm going to open up another poll. So the question is, uh, how many YouTube videos do you think we stream in 1 minute across the globe? It's just an average. So the average number of YouTube videos that we uh, that we sorry, yeah, that we stream every in 1 minute. Right. So there are multiple options. 1 million, 1 million to 2 million, 2 million to 3 million, 3 to 4, 4 to 5, and more than 5 million. Right. So you just make a guess. There's nothing hard and fast answer. So it's just your opinion. Yeah. Already we got 3 to 4 million. Any other opinions? All right. By the way, people who joined later on, you can scan the QR code, which will take you to this poll, and you can participate in this poll and view the results real time. So if you are wondering what this is something called Slido.com, which helps us give active polls in real time, and there are multiple templates they use. So if you want to use this for your presentations or classes, please feel free to use it. They have a basic version which doesn't require any payments, so that is cool. All right, so yeah, I think we have some basic participations. 50% out of 6 people think we watch more than 5 million YouTube videos in 1 minute of a day. So I'll give a few more seconds. All right, we have 10 participations. So again, I will keep this poll open. So if you want to participate anytime later on, please feel free to do it. So the answer is, we are not that lazy. It's just a joke. Please don't take it hard. We are not there yet to watch more than 5 million YouTube videos in every minute. So the answer is here. People who polled between 3 million and 4 million. Congratulations, you're right. So you can see, how much data is pouring in to the internet every minute. Now, this analysis was taken back in 2024, and you can see, different metrics, right? So, 3.4 million YouTube videos. This is all the statistics collected for 1 minute on average every day. Right. So 3.4 million YouTube videos. There was another big one, yeah, 139 million reels played on Facebook and Instagram, 251 million emails sent. Other interesting facts would be around 1 million messages sent on Slack, and the number of steps average Americans take in one day. I mean, in 1 minute. And also there was another thing that I found it very interesting. There was compromised. Yeah, 4,000 records compromised in data breaches every minute. So this also says, how insecure the internet is, and how bad it looks when we store our data, passwords and emails on the internet. Right. So we still got some work to do over there. So with the development of internet and a lot of usage of internet, people started emphasizing big data so much, right? So they called it as big data just because the data is so huge, and it's very hard to process all of them and find useful information. Now these days, it's getting so normalized, where it makes no sense to call big data as big data, just because all research that I know of is using huge amounts of data. So it is assumed that whatever applications we develop, the data is big, right? So we are not using the term big data. Of course, we can use it, but it is mostly assumed that whatever data we use these days are big, right? So they are big and volume. So being talked about volume, there are other definitions of big data. I know there is no defined set of words to define big data. Right. So there is no one sentence which can define big data. Big data mostly they can be characterized by these V's. Most people use three V's: volume, velocity, and variety. Nowadays people are increasing the number of V's to 5 and 7, right? But basically the three V's, volume, velocity, and variety, defines a big data. So it's just not the volume, but also the rate of data coming in, and also the type of data sets that are coming in from internet or from other applications or organizations. Right, the variety could be text, video, audio, I don't know, graphs, signals, whatever different types of data that you can think of. Right. The problem becomes a big data problem, when the traditional computers, they cannot handle the normal way of collecting, storing, analyzing, and sharing the data. Right. So when our traditional computers, like our laptops and our desktops, when they cannot handle the collection, storage, analysis, and sharing of the data, then it's a big data problem. So for that problem, we may need systems like high performance computers and supercomputers to do the analysis and get results for us. Right. But these days, big data is getting normalized, as I said, just because our number of transistors and our processor powers storage capacity is increasing every year. So we are getting used to it. So I still remember when I was doing bachelor's and master's, uh, getting 8 GB laptop would be more fancy, right? Nowadays people are going with 32 GB and 64 GB. I think 16 GB is getting more normalized among at least the American kids. So our capacity to handle large data is also increasing. Normally, it is better to have more data than less data. Why? Because it gives some flexibility for analysts, right? So we can analyze more portions of data. If we have only less data, we can understand only few things, and we can develop some hypothesis based on that small information, right? So if we have more data, it gives opportunities to explore more and more areas of the data, and it gives us more information too, and it helps to make those hypotheses better, and eventually we can also create better solutions with that, right? So that is the big data which we all be aware of, and that creates the necessity of high performance computing and supercomputing. There was one level before HPCs and supercomputers that were distributed computing and parallel processing. So distributed computing and parallel processing come, I think they were introduced a little before HPCs. So they can handle relatively small amount of data, right? So HPCs and supercomputers are designed for massive data sets, right? So distributed and parallel computer processing, they can handle a relatively small amount of data. And my definition of distributed computing comes only with the computers connected with our desktops and laptops, right? That could be distributed computing within HPCs too. Of course, they can handle very massive data sets, right? That creates a necessity of a high performance computing and supercomputers, and which make them ideal to handle large scale computations on very large data sets. Now We have big data, and we have HPCs and supercomputers, right? So what now? This is where things get a little tricky. Although HPCs and supercomputers are cool, they need more space, first of all, and more management for an organization to have. Right, and also these HPCs and supercomputers are not accessible for for many people, right? So most of the people would like to learn something, and some would be independent researchers. So for them, access to HPCs and supercomputers are impossible. So to mitigate those problems, some types of computing methods were introduced. That is cloud computing, edge computing, fog computing, and ubiquitous computing. Right. Some of this would be well known to everyone, like cloud computing, fog computing, and even edge computing. So we will look at what ubiquitous computing is. So they want uh, these modern computing paradigms to be present at the palm of human beings, right? So it should be accessible for everyone, and it should be very easy to access as well, right? So that is the main purpose of introducing these computing paradigms. Of course, they want to support big data processing. Of course, they want to make it more reliable and safe, secure, all that. But the ideal goal is to take large large processing and make it available for all common people in this world. First one is cloud computing. Cloud computing, as we all know, we may be aware of AWS, Microsoft Azure, and Google platform. They provide different types of services like software as a service, platform as a service, and infrastructure as service. Right. These are hierarchical. Software is nothing but let's say, for example, a pre-trained model, language model that you want to access, let's say a chat gpt, and you want to interact with a chat gpt. Let's say we are developing a chatbot, and we want to use gpt 3.5 or 4 as a backbone, and want to build chat gpt, I mean, want to build a chatbot from that. So in that case, we can simply access the software, that is GPT-4 in this case, from AWS or Microsoft Azure, and we just simply query them to access. Uh, if you go to the infrastructure, the lower level of hierarchy, we are giving the entire infrastructure, the compute nodes, their network, everything as service, right? So we are giving those resources to people who request or subscribe for. Right. So these services, of course, are not hosted on any place near to where we stay. Right. So they could be hosted somewhere far away, where they could use, acres of land for setting up data lakes and supercomputers and HPCs. Right. And they host these services in those big servers, right? And we can subscribe for AWS or Microsoft Azure, and request that we need, let's say, software. We need GPT-4 as a service, right? So we can pay for that service, and they just give us those services, right? So that's where this pay-per-use model comes in for cloud computing, right? So we just need to pay for whatever we are using, uh, but not the entire resources. So let's say, for example, they could charge us for every prompt we are submitting for the chat GPT or GPT-4 that we subscribe for. And similarly, for a platform as a service, we can request multiple compute nodes. Let's say, for example, with MapReduce or with Apache Spark pre-installed, and every request we submit, every command, Hadoop command or Spark command we submit to AWS, they will be charged, and also the number of amount of resources like memory and the storage we are using in AWS every minute or every hour. Right. So that is the pay per use model. It's mostly like renting out our resources, computing resources to people, and people can use those. I mean, rent those resources for their computation purposes. Now, this makes the system very easy to access. Of course, we need to pay for this, but if you compare this payment with we setting up resources that are required for our research and data analysis, and this payment would be a little cheaper compared to that. So that's the whole idea of cloud computing, and also cloud computing reduces the requirement necessity on equipment storage and maintenance cost, right? So having HPCs and supercomputers or even remote servers are cool, but we need to maintain it, update it, upgrade it all the time. So we need to appoint like a separate person to handle all those, right? So I'm having servers and I'm having a cluster in HPC, so I know how this works and how complex that looks like, right? So that'll be constant upgrades and updates going on all the time, which will be a little painful to follow up, right? Thankfully, we have a staff to manage all those, so our life is a bit free. But other than that, managing those big machines and clusters is painful. Now, we will go to the fog computing next. So instead, I will talk about edge computing, then go to fog computing because that makes things a bit clear for everyone. So cloud computing is cool. Cloud computing so far, yeah, we are providing large machines to people, and they can rent out, use them, and make payments, uh, which reduces management issues and storage issues and all that. But they come with problems too. Now they are connected with networks. We should submit our request, and that request should be transferred back to the HPC installed at AWS or Azure, right? So that would be a latency. That would be a slow in response, right? And also privacy concerns. Of course, we are giving our data and programs and everything to a third party, so that increases privacy concerns. So if AWS or Microsoft Azure, at least one part of your cluster is compromised, then you can think of how many people will get affected because of that, right? So that is always privacy concerns. Luckily, we have never seen any of those issues because they are tech giants and they can manage on those things relatively easily. So because of latency, they could be very less responsive, right? So you know our the researchers and their next goal after cloud computing was, why not make this whole process a bit efficient? Yeah, you are renting out resources and all that, but why not doing this bit efficiently? Why not move the computing close to the people who are using, right? So why should we move computing to to the people who are close to running those computations? Just because of the sheer volume and velocity of data that is coming from IoT devices and internet, right? So if we can collect, process, analyze, and store these data locally, then the computations could be made a little efficient, and the edge devices, that is our laptops or mobile phones or sensors, could run basic analysis on the data collected and send the summarized data or summarized analysis, whatever stored in the cloud. Right. So that makes things bit efficient. So this reduces overall overall transportation, overall amount of data that is being transferred over the internet and so on. So, um, so this makes things a lot easier, and it kind of reduces the capacity of reduces the challenges in internet networks and computer networks and so on. So this helps. Edge computing helps in real-time AI, since the computation is happening nearby the people who are using it. You know, the results could be real time. We can actually interact with the edge devices and get results. Right. And the best examples would be real time AI. We will come to this topic a little bit later. But autonomous vehicles is another very good example. Smart health, where people monitor patients through some sensors, is also a very good example of edge computing. So now with smart health, the sensors collect patients' data. They do the process on their own and store the analysis. Right. So later on, the doctor can analyze what's going on and take required actions. So although this is also cool, there is also some problems, like it's not easily scalable, and it's really not that flexible, right? So we cannot simply add more compute nodes to the edge and make them connected and make them work seamlessly, right? So that is not easily possible with edge. So which is not the case with cloud computing. We can easily add another node to the cluster, and they will just work fine. Right. So next is the fog computing. Fog computing is very simple. Think of fog computing as a small HPC between the cloud and edge devices. Right. So fog nodes would be very less in size, not that big compared to the cloud data centers. But instead, we will have a small cluster sitting in between. For example, each district may have their own fog nodes, right? So all the computations happening on edge devices would be sent to fog, and the fog could communicate between edge devices and the cloud devices. Right. So that is fog computing, and the next one comes the ubiquitous computing. Right. The ubiquitous computing is kind of interesting, and people are using them in real time without knowing that they are actually processed and ubiquitous computing. Right. The best examples are smart home devices, be it Alexa or Google Home or I don't know, smart monitoring systems or smart thermostats, whatever, right? So they're actually present in the environment, and they will be readily available to interact with humans, right? So they provide continuous services, they process continuous information and communicate with humans. And this is where the edge and the ubiquitous computing collaborate and offer very good resources for efficient AI and even autonomous vehicles. So ubiquitous computing, it's a little different from edge computing. The only difference is the device will be readily available for making communications. So that was the end of different types of computing. There are multiple caveats present within computing, right? So as the principal explained, it brings more energy and more water for running these computers, right? So it requires uh, I read somewhere, I'm not sure if that is true, but these HPCs and supercomputers drink billions of gallons of water, fresh water, every day or every week, right? So that is a lot of fresh water used for HPCs, right? So you think of how what's the price of 1 liter water bottle, right? So now compare that with the billions of liters of water consumed by these HPCs and supercomputers, right? So they are not so very efficient, and just building up or adding more resources is not a viable and sustainable solution. Right. That is one challenge we have right in front of us. It depends on what we are going to do in another 5 to 10 years. That decides the future of this future of our world. Right. So that is one big challenge. And as I said before, end of Moore's law is not good. Right. Although we are making the hypothesis false, we need solution to handle more data for computing purposes. Right. The next one is, of course, security. Um, as more people use big data, internet, and AI online, it gets really challenging to keep all data and all processes safe. Right. It's always threats pop up, always bad people chime in and try to disturb the overall system that we are using. So improving security and privacy measures is another priority we should always have. Whatever computing it is, be it supercomputers, be it quantum computers, or whatever we go, we need security and privacy measures, right? And the third one and the last one is actually developing on networks, right? So our yeah, we have 5G internet, and we are progressing good on 6G, but I think the pace should be a little high to make up for the communication of data between edge devices and the cloud, right? So the current network systems cannot be sustainable for another decade if we are not fast enough, right? So I think 6G is doing good. They will be publicly available, I think, by 2030 approximately. That's what I envision. So let's see what happens. But we need more efficient networks, faster networks to transport our data sets to a centralized location. Right. Now, these are all some emerging computing methods that I could think of. These are some basic ones, and um, out for research for more than a decade now. So there is a good number of progress on this side. Now the future is again integrating computing with AI, right? So I cannot think of the future computing without talking about AI, right? Now I have a very interesting poll set up for you all, right? The poll is for define what an AI is, right? So I have set up this poll. So I will stop the first poll, and I will, sorry, and I will start the second poll, right? So what is the best example of AI that you can think of? There are several scenarios I've listed over here, right? It's more like different systems, right? So first, for example, a humanoid robot is in a shopping mall interacting with customers, read them, answer their questions in a human-like manner, right? So which of the following do you think is the best example of AI, right? So what is an AI basically, and how can you transfer that definition to one of these scenarios? So let me know your opinion, right? Yeah, one participant says all the above. Okay. Again, our opinions on AI could be very different, right? Based on how we interact with these systems um, and what applications, AI applications we use, and uh, what people have been calling a system as AI in the past years, right? So our opinions could differ, but that is one reason why AI was introduced, right? So that is the most important thing, and that is not being followed mostly these days. So let me give you few more seconds. Let's see how this poll comes out, and see. Again, to emphasize, all of these could be AI, right? So it can be true. All these systems are AI, but that is one answer which defines a hardcore AI. So yeah, I think most people think it's all the above, um, and few think it's the AI system that analyzes market trends and make investment decisions, uh, um, minimizing returns. Right. All right. Um, all right. So yeah, there is no hard and fast answers for this definition. But the actual definition of AI is to develop a system that performs a human task in a rational way, right? AI could be you can different four types of AI. AI that thinks like human, AI that acts like human, AI that thinks rationally like human, AI that acts rationally like human. Right. So the term rational is very important over here. Why? Because humans can make mistakes, right? So human can be selfish sometimes. So we don't want the AI to replicate that. So that's why the rational comes in. If we can develop an AI system that does better than humans in terms of intelligence, then that is the perfect AI. So, but unfortunately, we were introduced to AI in a very bad way, particularly with movies like Terminator and 2001: Space Odyssey. All AI systems that we can think of tells one thing, it ends humans. No, that is very harsh, and it is not true. Right. So AIs they cannot end humans, and I would say they cannot take away human jobs. Right. So they are just tools, and AI lose purposes without humans. Right. So that is not completely true, or at least for a few centuries, it cannot be true. Right. So AI, it's uh, relatively new field compared to other research areas, particularly how it expanded over domains, with domains like natural language processing, IoT, robotics, social network analysis, machine translation, graph analysis, deep learning, and so on. Right. So it's a very vast area of research. Right. So where do we see AI these days? Again, that would be a lot of applications that you can think of. I just listed few that I saw in real time. There is this cab called Waymo running in San Francisco. Some people may be aware of this. This is a self-driving car, and they have cameras all around the car, which keeps monitoring what's going on around the car, monitoring for other cars, monitoring for pedestrians, monitoring any obstructions in the road, and so on. Right. So they do real-time detection using these cameras, and the cars use these detection methods to steer the vehicle and to give safe transportation for its passengers. Right. So this is the best example for AI because it avoids hitting passengers and make sure we travel safe in a decent speed. It cannot go super fast, and it cannot travel outside the boundary also. So that's why it's not very readily available outside San Francisco. The usage is limited to a city whose demographics or whose physical plan will not change relatively quickly. Right. The next example, of course, we all know ChatGPT and Gemini. So it's really fascinating to see how computers can, talk like humans or generate text like humans. So that is relatively a best example of AI. Of course, they have some problems, which we will come to later on. And the next one is deepfake. Deepfake is both good and bad. When it comes to security and privacy, yeah, deepfake is it's kind of scary, but it's available now. We need to think of what we can do. But the invention is good, right? So invention is really fascinating to morph one person as another person. So just a cool invention, which is really helpful in entertainment fields, and even if we use it for good, we can use it for education, for online tutoring, and so on. Right, so which is really good. There are key components in AI, components like machine learning, natural language processing, computer vision, robotics, and expert systems. These are all the key components. Without these, AI could not exist, right? So these are all some top domains which AI people work on these days. Particularly robotics, NLP, computer vision is so hard these days. More people, researchers I'm talking about, are working on these three domains, which is going much faster pace in conferences and journals at least. Now, let me explain what we do with AI. So my lab has a few grad students, and they are involved with different problems. So one of the good problems that we are working on is creating ethical LLMs. We are working with political scientists and linguists to do this, right? So the language models like ChatGPT could be, really biased towards certain demographic of people. In our case, we are exploring how biased these language models could get in terms of politics. As you all know, U.S. politics have two sides, Democrats left and Republicans on the right. Right. People have proved that most of the language models are inclined towards left. They kind of, incline towards Democratic parties. But it is not fair for an AI model to get biased like that. We want AI models to explain both, to look at both views, like left views and right views, and come to a conclusion, which is fair and which is more useful for human beings. But unfortunately, that's not the case. As you can see, they are all distributed. They have analysis from multiple language models, and you can see the distribution, how they are falling into. Some models are inclined towards left, and some models are inclined towards the right. So which is not so cool. So we are kind of finding the reason for this. Why they are actually inclining towards one side of the party. Right. So, and eventually we need some ways to mitigate this problem, because we cannot keep our language models kind of politically biased, right? And this is just for political bias. So this kind of bias is available for gender, race, religion, and even with countries, right? So this is not good for a language model, particularly an AI system. The second research that is currently going on is something that we work together with the physicists. So in the large uh, hadron colliders, they collide protons, right? Proton and proton collide, and study the emissions, right? So the main reason to do that is to study how our universe originated, and can we identify uh, any new interesting interactions happening, and can we find any new particles emerging from that interaction? Right. So it is a very hard problem because the data is so huge, and you can think of how many light emissions can be possible, and how they could interact and give out several billion emissions. Right. So not all collisions will be very interesting. Right. So there will be some collisions which will give out meaningful emissions, right? So interesting emissions, we call that as signals, and 90 to 95 percentage of the emissions will be noises, right? So the AI systems should mitigate those noises and identify the signal. That is the main problem we are working on, and it's an emerging problem. No, there is no one solution to do this. So we are kind of working on this to see if we can develop any AI models to identify these signals and mitigate or reduce the noises that were emitted from these proton-proton collisions. And these works were supported by National Science Foundation and the U.S. Department of Energy. Now, that is a quick icebreaker. We are almost at the mid of um, uh, almost at the mid of my presentation. So I just want to know what's your energy level, so that I can make this talk a little funny or make it more serious. So if you can participate, I think that'll be helpful. So I will leave the poll open. I will come back to this later. So I'll give a few seconds for you to scan the QR code and participate. Uh, so let's see. All right, I will let you guys participate in this poll, and I will continue with this with the talk. Since we are running out of time, I will try to move fast and finish all the slides that I created. So now it comes to the point, why AI matters to computing, right? So if you look at types of AI, we are in fact at the mid level of AIs, right? So initially we created very weak AIs like chatbots that could just reply to our questions, but does nothing more. And then we created strong AIs like ChatGPT that could learn, reason, adapt, and evolve. Still, it's not at its prime stage yet. So hopefully, we will fix all the issues, not just in generative AI, but in all AI that we are thinking of, and fix those. So we will have strong AI models in possibly another decade, and all these AI models could do intellectual tasks that humans can do, right? And the next comes the super AI, which is the real definition of AI. So, which is just in theory these days. We don't have a system that surpasses human intelligence in most of the times, right? So, and we are also having people who work really hard to make sure AI doesn't surpass their intelligence. So, kudos to them. But that is just in theory these days, but maybe possible once we are successful with developing strong AIs, right? So AI could interact with computing in many ways, right? Infusion of AI could increase efficiency, optimization, decision making, and also also creates AI democratization. We can make AI available to pretty much everyone. Not just for rich people, but also for a common man present in countries, right? So democratization is very important to make AI readily available and to also solve the purpose of AI. It should be available to everyone, not just for a few people who can pay for it. Right? So infusion of AI in computing can also increase how these systems work efficiently. AI could improve optimizations and much more. Right. Also, it enables moonshot ideas. Very fascinating ideas on how we can proceed after Moore's law has come to an end. Right. So we need more efficient ways to store data, find out which data is important, which is not important, improving personalization. So that's where the federated AI comes in. We need to give importance to privacy and security. So it's better to run AI models close to where people are, and not share the details with anyone. Right. So the federated AI is also a very interesting field that is emerging, and AI computing in all aspects of our lives. Whatever simple tasks that we do, be it turning on light or be it sweeping the floor or washing our dishes, can we make them all AI? Those are all some interesting ideas that are emerging, and people are actually working on these ideas too. And finally, AI as a service is an interesting idea. I think that is coming out super fast. So, how about providing AI itself, whatever AI model you can think of? We publish them as a service in a cloud, and people can rent them and use them. So they enhance resource management. They reduces human effort in monitoring systems and monitoring errors. And also anomaly and threat detection is one of the popular areas where they integrate AI in systems and in networks. Of course, we talked about personalization and integrating trained AI models to the businesses with AI as a service. Edge AI is another very important resource coming out. Edge devices are getting more popular these days. So running an AI model is not that simple on edge devices because they have very small memory and the storage. So how to make the big AI model compact and deploy them on each devices would be a challenge. So but that's why it's a very popular research, and people are working on different applications to make Edge AI possible. We are also kind of working on Edge AI at some level. So this work, which is supported by U.S. Department of Agriculture, we want to take real-time photos, taken by mobile phones and of plants and soil patches, and predict what their lifestyle, what their do they have any diseases, how much water it needs, and do we need to water this plant, and so on. Right. So ideally, our plan is to help farmers to for their irrigation. They can just take a mobile phone and take a picture, and our AI model will tell, what is the soil moisture, and what's the water content present for crops. Right, of course, the goal is to scale it to all common people, not just farmers, but if an enthusiastic gardener who wants to monitor their plants and water their plants, this type of model would be helpful. And now our idea is to deploy our AI model to mobile devices. To increase personalization. And we are particularly focusing on multimodal machine learning. So for now, we are just using tabular data, images, and time series data to do some forecasting and prediction. So eventually, our number of modalities would increase in the upcoming future. And right now, we are working on a very small scale with 3 farms and some bunch of data for our models. And we also are working on model compression. The model compression idea is very simple. The picture displayed over here is the best example of knowledge distillation. We develop one teacher model that is huge, and we also develop a student model that is small compared to the teacher model. Now, how in education the teachers help student learn something, that's the exact match for this knowledge distillation. So this teacher model helps the student model to gain the knowledge the teacher model gained, right? So on top of that, we can also add more data and more processing and optimization and improve this student model. Now the student model has its own knowledge and also knowledge from teacher. And now we have a smaller model that works like teacher or sometimes better than the teacher model. So that is also another research going on. So we are combining multimodal research with the model compression to make the processes a little efficient and suitable for edge devices. There are several limitations with AI. Now we talked about bias. Of course, we talked about making systems hot and requiring more water. That applies to AI as well. The prompts that we submit to ChatGPT or Gemini, it drinks up some amount of water. So that's what we can assume of, right? And AI weaponization is a really scary limitation, right? So the best example is deepfake, right? So deepfake, although it helps in entertainment domains, it's not so good when it comes to individual privacy and security, right? So making AI available to everyone is good, but at the same time, you also need to think of how to govern that, right? So each country should agree on a standard rules and regulations, and make it not possible to weaponize by an individual. And AI, currently we are more into Gen AI, but AI is much more than that. We have reasoning, we have non-generative machine learning, we have optimization. So all those are AI, and focusing on all these aspects equally is also very important. Not just on Gen AI, but the scope is still there. There are still people working on different domains. And finally, Edge AI. Edge AI is also a promising research area because reducing the size of a model is not very simple. Now we have seen DeepSeek, but we also need to see what are all the complexities people have gone through to make DeepSeek successful. It's not that simple. That's what I'm trying to say. So although DeepSeek is not or not an Edge AI, we can think of the complexities it would come with if we need to make the GPT as compact as possible so that it can adapt to small devices like mobile phones and cameras. Now, the future. So this is something I think of, right? So that's the start, right? It's not a real thing, right? So I'm not saying this will be the future. I'm just saying this can be the future, and this can be some of the computing methods that we will see in our lifetimes in the near future. All right. The first one is spatial AI. Spatial AI is nothing but, I will play this video. So you just watch. So the first one is spatial computing, and most of us will be aware of AI used in, artificial augmented reality, virtual reality, and extended reality, right? Um, this is promising research in several ways, and it's already helping people, particularly with health, medicine, and like you see, e-commerce and retail stores, in many possible ways. So there are still work to be done on integrating AI with the spatial computing, right? But only no, already no, there are fancy devices like Oculus invented. There are a few bad things like what the goggles, right? So particularly, I don't like goggles. We want something cool like what Iron Man wears. So that's what we are getting towards, but hopefully now we will be there in another few years. The next type of computing is quantum computing. I saw that there are good number of talks being uh, decided and planned out for the FDP program on quantum computing. So I will just touch base on what the quantum computing is. Hopefully, the other speakers can give you more idea on quantum computing. Right. So the classical traditional computer can are based on bits, right? So they can on or off. So zeros and ones, right? Which is kind of making things difficult these days. So we need something better than zeros and ones. So that's where the qubit comes in. So it's not just a binary anymore. That could be a state between 0 and 1, and this could allow us to store lots of data and process lots of data. Again, this is not that very simple. Managing quantum level information is super hard, and people are inventing many solutions to do that. So I will stop right there for quantum computing and talk more about other types of computing. The fascinating idea of neuromorphic computing is very interesting, right? So what is neuromorphic computing? We need to look at a few things like von Neumann's bottleneck. So von Neumann's design is something how we use computers these days. We have memory separately and we have storage separately, right? So that is a limitation. That is a latency for the communication between storage and the memory, right? So we are coming to the point where we are handling more number of data, and the constant communication between storage and the processor or the memory is not viable anymore. So we need to find an alternative solution. There is a fancy term called hardware lottery. Please take a look once this talk is over. There is a very interesting story behind this hardware lottery. So the hardware lottery just emphasizes, we need to find a solution where the research emphasis should happen equally on hardware, software, and also the algorithms. Algorithms, for example, machine learning. So that is the research of neuromorphic computing. They primarily they use silicon chips and microchips on computers, but instead of going with the traditional binary bits, they want to create processes, which kind of uses our brain neurons, right? How brain neurons take decisions or think of something in matter of milliseconds. So they develop spiking neurons instead of traditional zeros and ones, and they put together the memory and the storage in just one device. Now, this has some limitations, right? So, we are providing hardware, like the storage and processes in one chip. It gives responses in biological real time, but again, it will be dedicated for certain applications. For example, mimicking a part of the brain. All right. So that is cool, but it's also not scalable. So if our future is something where we have small devices equipped for different purposes, and we will be using those small devices for several applications like monitoring our health, or monitoring our homes, or monitoring the temperature and so on, then neuromorphic computing is the way to go. But the problem is, neuromorphic computing tries to mimic the brain actions, and we do not understand our brain 100%. So I think the brain research and also the neuromorphic computing should happen in parallel, and there should be communication between doctors and computer scientists to develop better neuromorphic computing. I will actually skip this video. Actually, there are two organizations developing neuromorphic chips. One is Intel, and there is a popular neuromorphic cluster setup. It's called Spinnaker. Please check out Spinnaker. It is a really fascinating idea on developing a neuromorphic computing. Oops. So the next one is biological computing. It's also called biocomputing, basically an extension of nanobiotechnology. Quantum computing can be another extension of nano biotechnology. But here, we use the biological molecules themselves, right? How cells interact with each other and how fast they can interact. So we create a cell or a biomolecule and design it in such a way that when they get some response, they give the output. It's more like how we design logic gates and logic systems, right? So we put a group of biomolecules together, and they are designed in some way. How we organize our logic gates to achieve a task, it's very similar to that, at least for now. Right. So these biomolecules will be organized in some manner, and they will be assigned some communication channels, like metabolic pathway logics, and when we give some input, they will give some response in very real time, right? So and it is in a very early stage of research, right? So there are very good potentials for this biocomputing, particularly the personalized drug discovery. Imagine a situation where we have an AI model like the biocomputing that gives a personalized recommendation on drugs based on our health records, based on our current health. It will give it will subscribe or prescribe drugs for us. So it helps in precision medicine. And our human biology has this beautiful system where it can make decisions using complex combinatorial problems. So whatever combinatorial problems we can think of for computer science, that can be solved relatively fast. And all the computing that we discussed so far, quantum computing, biological computing, neuromorphic computing, they consume very less energy compared to the traditional energy. So that is the boost, which kind of encourages other people to work on these type of computing. And they work on massive data, right? So their storage, the storage of data is a bit beyond bit system in these neuromorphic computing and biological computing. So the storage, processing, and analysis becomes very efficient, right? That is, and I will be skipping this video as well. There is this company called Final Spark. So they have they have published a platform called Neuro Platform, and they have this biological computing set with some 16 biomolecules in real time. So as researchers, we all can actually try to access this and find out what they do. But it's called Final Spark. If you just search on Google, you will find a lot of information on this. So this video particularly is interesting because they kind of designed a biological system that kind of make butterfly make its own decisions and to go to a flower or to fly away and so on. So they have made the butterfly's brain based on this biological computing. Then the next type of computing is called photonic computing. We talked about quantum bits, we talked about biomolecules. Now it comes to the part where it gets even fancier. We use light or any electromagnetic waves as our data, right? So using light has its own advantage, right? So you think of what's the rate the light travels and how we can use the light data to process, store, and analyze information. So this could be the future. No, we have not seen much work using light for the processes. So and using light as its data, could integrate well with all types of computing that we talked before, even with quantum computing. So, which is a really interesting field to look at. There's not much research done on photonic or optical computing, but it's kind of expensive and bit hard to explore at this point. But maybe future holds promising. Photonic computing will be possible. So that is my end of the talk, and just a couple more things. I'm always open for collaborations. So if you are interested in any of my research, be it multimodal machine learning or the work that we do with physics or ethical language models, please feel free to email me. I will put my email in the last slide. And if you think you have any potential bachelor student who are interested and enthusiastic on machine learning and AI, and if they want to do PhD, please let them contact me. And there are scholarships available at OSU, and they can do better research over here. So these are all my contact details, and there is a small poll open just to get a review and feedback for my talk. If you can participate in that, I know that'll be cool. So yeah, thanks once again for inviting me to give this talk. I hope some of these information will be useful. And thank you. Have a wonderful evening. If you have any questions, I'm pretty open to answer those. Thank you.
Thank you, Dr. Bagavathi, for your inspiring speech on the given topic. We extend a heartfelt gratitude to Dr. Arun Bagavathi for delivering an enlightening session on exploring the future, Introduction to Advanced Computing Paradigm, as part of our faculty development program on supercomputing. Now, if any attendees are interested in interacting with Dr. Arun Bagavathi, they are requested to raise their hand so that our team can unmute them.
Good evening, sir. For you, it's good morning, I think.
Yeah, hi.
Hi, sir. This is Murali Bhaskaran from Rajalakshmi Engineering College, Chennai.
Yeah, hello.
Very interesting your presentation. One point that agricultural, are you in the Oklahoma state, do you have agriculture for establishing such a development, or it's a simulating one?
So yeah, Oklahoma is basically a rural state. So there are lots of agricultural activities going on. They actually have a big research center studying, crops and when to plant them, monitoring their health, and so on. So we collaborate with the Department of Agriculture at OSU to do our work. But we are not there yet to deploy our models to say farmers or any common man, because it's not fully developed yet, and we are kind of working towards that. We are constantly interacting with farmers on what they really look for from for, let's say, for example, a software application, right? So what will be very easy for them, and how it will be helpful if they have some prediction or forecasting models from AI. So I don't know if that answers your question, but I'll
Yes,
be
sir. Yes, sir.
happy
Actually, my doubt is what type of major cultivation and for what plant you are supporting for them, like that. It's a plant based or it is a generic. We cannot give generic way of application solution for them. It's a what type of cultivate they are doing. Based on that only we can help them, I think so.
Yeah.
My question is what type of plant you are helping them, like that.
For now, we are focusing on corn and wheat.
Oh.
Yeah, but yeah, the
One
vision
more.
is to make a generalized model to support wide range of crops. But yeah, for now we are focusing on corn and wheat.
One more question, sir. Sorry, the listeners. Actually, still we are worried how to utilize the supercomputer or high performance computer in education system. You told that in your university you are having the supercomputer, but in India many universities will not have the, except the Indian Institute of Science and Pune, something like. Other universities are using the standalone or some server is there. What type of application we need a supercomputer? Whether you need huge data or our processing algorithm should be very big. The number of lines of codes, whether it's a number of lines of codes or the data. So just you can throw light on it, sir.
It's kind of mixed according to me. Mostly it's data, right? So data is what we pre-process and analyze in the first level, right? So if our data is big, for example, most of our HPC is being utilized by bioinformatics or people who study, genomes and metagenome, because we have very huge amount of data. So mostly they use HPC. right? So the data that we are using is, for computer vision or language models would be, few gigabytes maybe. That that is at least in the research level, right? So that amount of data is enough for us to work on research and introduce a model. But ideally, yeah, if the data is big, we need HPCs. But I always advise my students to use their personal computers as much as possible. Because we have powerful systems these days. 16 gigabytes of RAM is super useful, and they have GPUs most commonly these days in all the computers. So that's what I advise. So if they get more data, like terabytes of data to analyze, and they have like big models like GPT 4, for example. GPT-4 is very resource heavy, so they cannot be processed in their local machines because their RAM will not simply support that. So if their model is big, then we need definitely HPCs and supercomputer to have. But if the model is native or traditional algorithms like CNN and RNNs, then I think personal computers should be fine.